All right, so today we're going to continue kind of in the same vein as the electrolytes, talking about fluid balance and kind of how the electrolytes help out with that. So specifically, we're going to go through a whole bunch of different things with fluid balance. So first of all, just talking about the basics, kind of almost going back to probably a lot of the stuff that you did in your physiology classes, so osmotic pressure and filtration forces, just kind of going into how blood and water distribution is regulated. We're also going to talk about how the kidney regulates this. We're going to talk a little bit too about why salt sensitive people are kind of more at risk of having high blood pressure compared to the average population if they eat a high salt diet. And then we're also going to talk about kind of fluid needs during exercise. So to start out just with some basics here, just remember that water accounts for about 60% of total body weight. So that's about 42 liters of water in 70 kilograms, so kind of like an average sized person. So that's a lot. So more than half of our weight is just water. And then water serves as a medium for the solubilization of nutrients. I always have problems pronouncing that. And then it's also a medium for metabolic reactions. And then also just to remind you, remember we find water in two major reservoirs. The first one is intracellular, so that's really water within our cells. And then there's also the other one is the extracellular water, so anything outside. And interestingly, most of our water is actually in our cells. So it's not like in our blood or, you would think blood would be a major component of water, but it's actually pretty small in comparison to how much just sheer fluid and water we actually contain within our cells. So it's actually, if you look at the amount of liters, it's actually about twice as much is contained within body cells compared to just outside the cells. And then looking more into now outside the cells, so the extracellular reservoir, that's actually divided into two components. So first you have your plasma. So that's really like your typical, just your blood, ending, of course, at your capillaries. And then there's also the interstitial fluid. So remember, interstitial fluid is all that fluid kind of between the capillaries and the cells. So that's kind of like this green area here. But then interstitial fluid is also all this, the fluid between cells. So any kind of between, in this picture, anything that's kind of between, that's all the interstitial fluid between cells and then between the blood supply and the cells itself. So again, kind of looking at a breakdown of how much is where. So fluid compartment values. So remember, percentage, if we just look at this percentage column, remember total body water, about 60%. Extracellular water, so that's the stuff that's basically, again, outside the cells. So most of it, I just want to point out, is actually interstitial fluid. So the blood actually accounts for only about 5% of our percentage of fluid of our total body weight. So I don't know, I always thought, we have a lot of blood in our bodies, so that would account for a pretty major component, but it's actually not that much, just 5 out of 60. And then the intracellular, so that's stuff that's in the cells, that's about 40%. But yeah, interstitial fluid for extracellular is kind of the major compartment. Sources of water, just talking about kind of where we're getting water from. Obviously, fluid intake is our major source. So the average person consumes a little over 2 liters. And I'm pretty familiar with liters being Canadian, but if you don't know what a liter, if it's hard to kind of conceptualize, a liter is almost the same as a quart. So if you kind of can see that amount. So we need about 2.5 quarts basically of water a day. And that, that would change obviously with like different climates, if it's super hot, and then also if you're like exercising a lot. But in general, if you're kind of just going about your normal day, not exercising that much in a temperature controlled environment, most people, yeah, consume about a little over 2 liters or a little over 2 quarts. And, there's that whole thing. People always ask me, like, well, why do we need 8 glasses of water a day? And honestly, I have no idea where that came from. It's kind of eight glasses or 8 cups of water is basically 2 liters. So maybe that's where it came from, but I don't know. I know that's kind of like just what people follow, but really, it doesn't really matter. And it's for fluid intake too. It's obviously best if it's from a straight water source, but that also counts if you, are just taking in like tea and coffee and stuff like that. The other thing too is we make water basically from metabolic processes. So that's 10% of our daily available water. And that's like any of those things where you're like making water as like in any metabolic process. Like when we were looking at different, basically metabolism in general, you'd see that water or H2O would be a byproduct of that, of any of the kind of like reactions that we looked at. So that's what this is talking about. It's basically water as a byproduct of metabolic reactions. But that's actually a pretty sizable amount. It's about 10% of our daily water. So sources of water loss. So we just talked about intake. So how do we actually kind of get rid of pretty much that same amount of water, 2,300 milliliters per day? Obviously, most of that's with urine, something that you definitely probably knew already. So 1,400 milliliters. If you're not kind of sweating excessively, but just day to day, you'd lose about 100 milliliters of water per day. We actually lose about 200 milliliters through fecal excretion. And then the other kind of major component that you probably don't think of a lot is 600 milliliters are lost through insensible water loss. So that's like evaporation from your respiratory tract. So every time you're breathing, you're also losing a little bit of water. And then also just general diffusion through the skin, which just happens all day. So that's, all those components basically add up to the 2,300. And that's how we, basically lose water. So now to kind of get into a little bit more of how water distribution is regulated throughout the body. And first starting very basically with osmosis. So remember from basically high school biology that water moves from a more dilute solution to a more concentrated solution across a semi-permeable membrane. And so that's basically, and also remember the membrane's permeable to water, but not to the solutes. So all osmosis is say you have like, these are your solutes. There are, just a couple of these over here floating around in this much water. Then there's a whole bunch more solutes over here. What's going to happen, what osmosis wants to do is shift more water to a more highly concentrated area. So basically the concentrations equalize. So you're going to have the same amount of water per solute as you would on this side and that side. It's basically all osmosis is. And then again, probably a review from your physiology lectures, but what is osmotic pressure then? So osmosis can be blocked by applying external pressure to a semi-permeable membrane. So here, this is just kind of a different way of showing that. Here's the solutes floating around, and then water would basically want to move in here to make sure that there's a certain amount of, that the concentrations are the same. And so osmotic pressure is the amount of pressure required to exactly oppose osmosis or water movement across the semi-permeable membrane. So again, more water wants to shift in here, just making sure that all these solutes are at a certain concentration. But then you can stop that by basically applying pressure or having some type of pressure on this membrane to basically stop that flow of water from going here to here. And then the reason I'm talking about all this is because this plays a really important role in fluid balance in our body. So what I'm trying to show you here, this is your blood. So let's say this is your capillary. This is the fluid between your blood vessel, so the capillary, and your tissue cells. So blood vessel, interstitial fluid, that little bit of space fluid between the blood and then the tissue cells. So one thing to remember is that proteins are found in much higher concentrations in the blood, so in the plasma, versus the interstitial fluid. So these little circles here are the proteins. So yeah, much higher amounts in the blood than in the interstitial fluid. And these proteins are just too big, so they can't permeate the capillary endothelium. They can't kind of, with osmosis, or basically these little guys want to get over there, but they can't. They're just too big. They can't get through here. And it's actually these proteins that are the main things that establish osmotic pressure between plasma and interstitial fluid, because the proteins attract water. So basically, again, let me just say that one more time. So since there's a lot more proteins in plasma, these little guys, these proteins, attract water. So then they are the things that establish that osmotic pressure. They're the reason that water is not just constantly kind of like shifting over to here. And yeah, that's basically the proteins that are attracting water, and they are establishing the osmotic pressure between the plasma and the interstitial fluid. And this all plays a really important role in basically filtration forces and the movement of water from plasma into interstitial fluid. So the next question is, well, we just talked about how these proteins attract water. So water kind of stays over on this side, and that's osmotic pressure. But then we all know that basically water, fluids need to get out of our blood vessels into the interstitial fluid and eventually into the cells. So how do we actually get water out of our capillaries? Excuse me. So this movement is accomplished by something we call the filtration force. So filtration force is basically that force that moves water from the blood, plasma, to the interstitial fluid, ISF, interstitial fluid. And what actually does that is just the pumping of the heart and blood pressure. So again, probably back to your physiology lectures, remember, blood pressure makes water move out of the capillaries, whereas osmotic pressure keeps water in the capillaries. So osmotic pressure is all those proteins attracting water, keeps them in there, but the blood pressure, the heart pumping and the blood pressure can be so strong that it actually forces that fluid out. So another thing that I want to show you in here is that it's showing you the capillary here. Just pay attention. This is the arterial end, so the part coming from the heart. And this is the venous end of the capillary, so the one returning to the heart. So at the arterial end, so talking about this side first, blood pressure is stronger than the osmotic pressure. So that's what is then causing that water to move out of the capillary. So this is just trying to show you fluid is moving out on the arterial end, the part coming with like basically fresh blood from the heart. The venous end on the other side, the osmotic pressure, so all those little proteins that like to hold on to water, that pressure on this side is much stronger than blood pressure. So that helps keep or basically force water back into the capillary. So that's pretty much what filtration forces are. Blood pressure on the arterial end are stronger, so then water can move out, supply cells with fresh oxygen and blood. And then on the venous end, when it's returning back to the heart, the osmotic pressure is a lot stronger. So fluids move back in and then return to the heart. So other important factors in fluid balance and compartmentalization. So we've talked about fluid intake and output, osmotic pressure and blood pressure. But just in general, I also want to go over how all this is regulated by the kidney. So as we know, the kidney produces urine. The kidney's super sensitive to fluctuations in diet and fluid intake. So our actual urine will, vary in consistency a lot over the course of the day. One thing I kind of wanted to know when I was putting these slides together was, well, how much do our kidneys actually filter a day? We know that we let go of, 1,400 milliliters per day. So here it is, 1,400 milliliters a day is on average what we kind of excrete through our urine. But I was interested to see, we filter 130 milliliters, or about half a cup of our blood every minute. So that's a ton. Our kidneys actually filter 187 liters or 187 quarts of blood or filtrate a day. So yeah, it's a lot. So basically we're constantly filtering this blood, but very little of it is actually excreted as urine. So definitely much less than 1%. And then also, these are all the things, like a lot of the minerals and stuff that we find in our urine. But do you know why urine is yellow? Some of you, when there's people in front of me, a couple people usually know the answer to this. But if you don't, basically urine is yellow because it contains this thing called urobilin. And urobilin is basically a byproduct of heme breakdown. So heme is broken down and then it turns into bilirubin. And then bilirubin is further broken down into urobilin. And urobilin gives, kind of our pee, that yellowish color. So just a review too on how the kidney regulates fluid balance. So fluid regulation. So starting kind of from the very bottom here. So the whole thing is activated when blood pressure falls. And I know we kind of did a basic version of this in the vitamin D lecture. So blood pressure falls. It causes the kidney, remember, to release renin. Renin then hydrolyzes angiotensinogen, which is a plasma protein made by the liver. So it causes this hydrolysis. Then angiotensinogen is formed and converted to angiotensin II by the action of angiotensin converting enzyme, or ACE. And then the product, so angiotensin II, making that is super important because it basically results in 3 different things happening. First, it acts on the brain to increase thirst. So if you increase thirst, obviously you increase fluid intake. And then when you increase fluid intake, you also increase your blood pressure because you have more fluid in your blood vessels, so that increases pressure. It then causes also the constriction of artery smooth muscles. So it causes your vessels to constrict a little bit more. That can also increase blood pressure. And then it also causes aldosterone release. So we've talked about aldosterone a little bit in our previous lecture on electrolytes. So what does aldosterone do to sodium? If you remember, it causes sodium to be retained. So here I show you salt and water retention. So it basically tells the kidney to not excrete sodium. Sodium is brought back into the body. And then the key thing, remember here, is that water follows salt. So if water follows salt, you're going to get more water in your blood vessels as well because there's more salt in there. And then you're going to increase your blood pressure. So, and then to also go into a bit more information or a bit more details on how aldosterone does this. So it actually has different effects on each electrolyte. So remember sodium, what does it do to that? Causes retention, goes back in the body. How about potassium? What did we talk about in our last lecture? Potassium, aldosterone causes potassium to be excreted. And then, I don't know if we mentioned chloride in our last lecture, but it does have an indirect effect on this. What do you remember most about chloride? It follows sodium. It's basically like sodium's little brother. It's wherever sodium goes, chloride goes too. So it kind of has an indirect effect where if sodium is reabsorbed, so is chloride. But let me show you in a bit more detail. So first, what does aldosterone do to sodium? So just explain this a little bit more. So this is the blood side. So this is going back into the body. This is the urine side. So that is what's getting excreted out of the body. So that might help if you kind of make some notes there. So aldosterone, the way that it kind of reabsorbs sodium is by activating a sodium potassium ATPase pump that is actually found on the nephron. So here's that ATPase pump on the nephron. So when it activates that, it basically, it's facing this way. So sodium is then reabsorbed into the body. And then since water follows sodium, water also just basically moves back in as well. In the case of potassium, remember these sodium potassium ATPase pumps, for when sodium comes in, that's always in exchange for potassium going out. So basically, when you activate the ATPase pump, the main thing is to like bring sodium back into the body. But every time you're reabsorbing sodium, you're also excreting potassium at the exact same time. So sodium in for potassium out. And that's what aldosterone does. It activates this, so sodium comes back into the body in exchange for potassium getting kicked out into the urine. And then in terms of chloride, remember, chloride just likes to follow sodium around. So it's kind of in the same foods as sodium, and then it likes to, if you remember, for absorption, it kind of creeps into the body between cells because it likes to follow sodium. But then it also follows sodium in terms of excretion as well. So aldosterone doesn't directly affect chloride. Chloride's not in this pump. But chloride simply follows sodium after it's absorbed into the blood, and it crosses the membrane by passive diffusion. So again, kind of like just follows sodium again back into the body. So just to summarize all these effects of aldosterone, for sodium, remember it increases reabsorption into the blood. And then the effect of that on fluid balance is that since water follows sodium, you have more water reabsorption, which leads to an increase in blood volume and blood pressure. In terms of potassium, it basically increases the excretion into urine. So you're letting go of more potassium in exchange for sodium. And the mechanism of this is actually kind of unclear. It's still unknown exactly how, the mechanism on blood pressure. That's one of the reasons why there's still AIs for potassium. We just don't know exactly what the effects on blood pressure are. So if you're excreting all this potassium, how does that affect blood pressure? We're still not sure. Chloride, remember, just follows sodium around. So aldosterone indirectly increases reabsorption into the blood, whereas chloride doesn't really, in terms of fluid balance, doesn't really have any effect that's known. So we've talked a lot about sodium being kind of reabsorbed, but how do you actually let go of sodium? How do you get sodium out of your body when your blood pressure is high enough, basically? So the way that this happens is that the heart will sense an increase in blood pressure, and then the heart is the actual organ that releases this hormone called ANH, or atrial natriuretic hormone. And ANH is the thing that actually promotes sodium excretion in the urine. So once that's released, basically once sodium's released, water again follows sodium into the urine, which then decreases your blood pressure. So it's actually done by, the heart sensing an elevation in blood pressure and then telling your kidneys to let go of sodium. So also, I just want to talk about kind of a bit more of the mechanisms. Remember in the last electrolyte lecture, I was saying that There's salt sensitive individuals. Do you remember how many people are salt sensitive? It's about 20% of the population in the US. So 1 out of 5 people are salt sensitive, which means if they consume kind of higher sodium diets, that their blood pressure will go up. But 4 out of 5 people, or 80% of people, can basically consume as much salt as they want and their blood pressure won't go up. So what is happening in these salt sensitive individuals? Why are they not dealing with sodium well? So what is actually happening? The first mechanism that's kind of not working properly in their bodies is that salt sensitive individuals have been shown to have problems excreting sodium. They actually have problems with this whole thing. They don't release enough of the ANH. Their heart is not sensing that enough. They do release a little bit, but it's just kind of in lower quantities than it should be. So they have problems excreting sodium, and so they're not excreting the proper amounts. And then therefore their blood pressure is going to remain high because there's going to be more sodium in their blood to attract water, which then increases blood pressure. The other thing that's happening in the bodies of salt-sensitive individuals is that they have increased cardiotonic steroid release. And so these are steroids that disrupt muscle contraction and basically lead to increased vasoconstriction. So not only are they not kind of letting go of sodium, so they have higher fluids, more fluids in their vessels, but then they also have basically higher vasoconstriction. So their blood vessels are constricting more than they should be. So both of these things have like compounding effects and then lead to problems with blood pressure control. And then I know we talked about this a bunch of times, but how does blood pressure actually lead to cardiovascular complications? So just to review this, remember with hypertension, blood is forced through the circulatory system at a very high pressure. And so when you have higher pressure, you basically have most of these proteins and all the different things found in blood kind of like zipping through here at really fast speeds. And then because they're traveling so fast, they have a much higher chance of kind of dinging or like, excuse me, I don't know what else to use, but like kind of scratching up the surface of the arteries. And then whenever you have these scratches, that's where the oxidized LDL likes to kind of accumulate. It finds these and then it tends to stick on to those little parts more. And then that all can lead to atherosclerosis or the eventual formation of plaques in the arteries. So lastly, I just want to talk about fluid intake during exercise. I'm sure you talked about this a lot more if you take the sports nutrition class, but this is just a basic overview for those of you who haven't taken these or, just want to know a little bit about it, but are not really interested in becoming kind of full-on sports nutritionists. So fluid intake during exercise, just remember, is super important because it helps maintain our body temperature and blood volume. Basically, we can't get rid of, when you're exercising, you're creating heat, and our body needs water to basically get rid of that heat and expel it, sweat. Helps cool down your body. So that's kind of the main thing that we're going to be talking about now. So sweating during exercise, first of all, what's happening there? So this is the primary way of dissipating that excess heat. And then if you're exercising at, if you're going on a run or something or on an elliptical machine or something at a pretty high intensity for an hour, you can lose about 1.5 liters per hour. So your body, if you're doing intensive exercise, can lose a lot. So again, that's like 1.5 quart of water just in an hour. And as I just mentioned, fluid needs are linked to energy expenditure. So remember, when you're exercising, you're expending energy, and then heat is a byproduct of energy expenditure. And we have to transfer that heat to our environment to maintain our body temperature. So the more heat that we expend, the more energy we expend, the higher the heat production, and then the greater our fluid needs. So you need all that to keep your body temperature at in a regular rate, or regular zone, I should say. So if no water is consumed during exercise, our body temperature will actually slowly rise. So, you get super thirsty while you're exercising, and that's just your body telling you, yeah, our body temperature is going to get super high unless you keep on drinking water. So we can keep on sweating and then basically dissipating this heat into our environment. So what can eventually happen actually is hyperthermia, which is when the body temperature exceeds 40 degrees Celsius. So that's about 104 Fahrenheit. So that can develop if you don't drink any water during exercise, and that eventually can be deadly. So in general, do you know what the kind of fatal body temperature is? Actually just looked it up. It's about 110. So, 104 is when you have a really extreme fever, but people usually die when it's 110. But some people have actually been alive or known to survive until 115. So, but in general, 104 is very, very high. Usually people are hospitalized at that point. So anyway, to explain this kind of graph, the whole reason I'm even showing you this. So this is a study that was done at UIC about 10 years ago or so. It was by a professor in the kinesiology department. And so he wanted to know, well, what happens if I give people that are exercising, doing stationary bike exercise for 2 hours, so over a 2-hour time frame, what happens if I give them different levels of fluid intake? So this group here, they got tons of water, more than what they needed. This group here got the amount of water that would just be needed to, in terms of replacing water loss. This one got slightly less than that, and then this group got absolutely no fluids during this 2-hour exercise session. And at the same time that these were actually students in the kinesiology department, so I don't know how much they got paid because the next part of this is kind of gruesome. So they actually they measured their body temperatures rectally. So they're basically, these poor students were like sitting on thermometers, like rectal thermometers, while sitting on these stationary bikes for 2 hours. So yeah, hopefully they got paid well. But what also, just the ethics of this seem a little crazy. I'm surprised that this actually passed the UIC IRB, but somehow it did. And so what he found after 2 hours, if he compared the group that got tons of water, so enough of their water needs, compared to the group that got no water, he found that over 2 hours, there was actually almost a full Celsius degree difference between that. So this is just to show you, if you're not taking in water at all, or if you're taking in kind of less than you need, your body temperature will increase. Whereas if you're taking in enough, it will increase very mildly, but it will still stay within the normal range. So in other words, super important to drink lots of fluids while you are exercising to basically keep your body temperature in a regular range. So let's talk a little bit about kind of how sweating helps basically cool down your body. I'm sure most of you already know this, but just to remember the mechanisms of this a bit. So muscular activity, starting here with number 1, increases body heat. So that's that whole energy expenditure thing we were talking about. Heat then stimulates the hypothalamus to basically stimulate, the hypothalamus then stimulates the sweat glands to secrete sweat or fluid. And then it's really that evaporation of fluid on the skin that cools the body. So you need water, basically intake of water, to constantly supply your body so your body can then sweat, so then it can cool your body and basically keep your body in a normal temperature range. So what happens if you don't drink fluids? I know we just talked about it a little bit, but if you want to know kind of percentage-wise, like percent fluid loss and the related disorders, so you can actually lose about 2% of your total body weight of water and still be kind of okay. You might feel like you have, most of the time you're still able, if you're running or something, your muscular endurance and power and strength probably won't be that affected with just 2% body weight loss of water. You might feel a little uncomfortable, a little hot, but that's pretty much all that's going on here. 4% though, when you lose kind of twice as much as that, that's when you're going to start to feel more tired if you're still running. So you're going to have reduced muscular endurance. When you already creep up all the way to 6% of water loss of total body weight, that's when you're going to have decreased strength, power, and endurance. Basically, it's going to be very difficult to continue. And then you definitely don't want to push it any further, because if you lose 8% of water total body weight, that's when you're actually going to get hypothermia. So that's when you get heat stroke, and that's when your body temperature will start creeping up beyond 40 degrees Celsius or 104 Fahrenheit, and that can be deadly. So you definitely want to replenish water, when you're still in this range or below, so none of the rest of this stuff happens. So how much water should we be taking in? I looked at the American College of Sports Medicine and some others just to kind of look at what they're recommending. But current recommendations suggest consuming 1 to 1.5 milliliters with each calorie expended. So that's in general. So let's say if you're running for an hour or something, that can burn, 400 to 500 calories. I guess it also depends on how big you are. But, most people that run burn about 500 calories an hour. So in order to replace, or the amount of water you should consume with that, is about 5 to 750 milliliters should be consumed. One other thing I want to mention, I think I mentioned it in the class before, but you really can't trust, like whenever you're in the gym and you see, if you're like on an elliptical machine or something at whatever gym you go to, if you go to a gym, they'll tell you how many calories you've expended, but those are generally lies. So please don't follow. It's just basically companies trying to sell stuff and basically show that their piece of gym equipment is helping you burn more calories. So I remember being on an elliptical machine in a gym a few years ago, and it told me that I burned 800 calories in an hour. And I was like, oh yeah, that's completely impossible. Like most people my size would burn, at most like 250 calories or something. Or, if I'm on a treadmill really running, maybe 400 to 500, but 800 is ridiculous. And then, these people will just go out after thinking that they burned 800 calories and then just like grab a milkshake or something and then just basically end up gaining weight from going to the gym because they think they burned off all these calories, but they haven't, and then they eat all this food. So when you want to look at the actual calorie expenditure, I would recommend looking at American College of Sports Medicine. They have some nice tables looking at like how much you burn on average. But again, obviously, if you're like a huge person, you're going to be burning a lot more calories than if you're a huge like muscular person than a smaller person with like less muscle mass. But those give you much better indicators than those pieces of gym equipment. So the ACSM recommendations for fluid consumption in general with exercise. So before you start exercising, they recommend drinking about 2 cups, so 500 milliliters, about 2 hours before, just to make sure that you're kind of like at a good hydration state before you start exercising. Fluid consumption during exercise, they say start drinking kind of early. You want to kind of take smaller sips of cool fluids regularly throughout. And then you want to try to replace fluids at a rate that equals water loss from sweating. Obviously, that's kind of hard to, that's kind of hard to measure if just in general. So you can kind of look again at those tables to see kind of how much energy is expended with whatever exercise you're doing, and then just multiply it by the 1 to 1.5 milliliters per calorie to get that. And then adding electrolytes, there's been a lot, I would probably talk to Kirsten more about the details of this, but from my understanding, if you're just going to the gym like once a day or something and doing kind of like a moderate intensity workout, you don't really need electrolytes. It's usually athletes and stuff that, sweat so much, or, if you're training for a marathon, absolutely, then you're going to need to replace electrolytes. But if it's just something where you're not working up that much of a sweat, you don't need electrolytes with just an hour of kind of moderate intensity exercise. So you don't really have to buy into all those products at that point. But yeah, obviously if you're an athlete or if you're training for something or really sweating a lot and losing a lot, then yes, then you would need like the Gatorades or whatever, any type of electrolyte replacement drinks. Fluid consumption after exercise, it's usually said, replace fluid losses if you didn't during exercise. So some people really don't like to drink if they're, just exercising for an hour. That's fine. You can also replace it after your exercise session. That's that big of a deal. So, but you know, obviously if you're doing something more extreme, then I would definitely recommend that you drink stuff during exercise. But again, you know, Kirsten is a sports nutritionist. She could definitely give you more information on that, or she probably did in her class. That's a lot more detailed than this, but these are kind of the basics. So yeah, Gatorade, not totally necessary unless you're doing kind of more extreme exercises. All right, great. So that's all I have for now. And yeah, I guess I'll see you guys at the next lecture or talk to you guys at the next lecture. All right.